Good day. I'm here to present our research paper, a deep learning approach for automatic scoliosis cub angle identification. So I'm Renato R. Maaliw on behalf of my co-authors. It's my honor to present this paper. So for the introduction, the spine is a critical part of the body, providing structural support, and it performs numerous essential roles. So scoliosis is a malformation of the spine characterized by the lateral curvature. Its prevalence is approximately 470 individuals to 5,200 for 100,000 of the population individuals worldwide. Its angles are generated by two tangent lines or the cub angle to identify the most tilted upper and lower vertebrae end plates. Traditional image analysis for scoliosis is a time-consuming and mechanical approach based on feature extraction. Physicians perform manual measurements, assessments, and identifications that presents several challenges. Because of anatomical variances, scoliosis identification makes it difficult in terms of precision and dependability to quantify the extent of the abnormalities. Moreover, instrumentation, vertebral movements, patient's posture, and positioning accounts to measurement errors. So based on literature, experts observe around up to 8-degree variation in terms of cub angle measurements using manual annotations. So what are we proposing? We're proposing an AI because it has a vast potential that can benefit medical diagnosis. It can pave the way for improved healthcare opportunities. As part of the Industry 4.0 revolution, it can assist with early, fast, and efficient diagnosis of X-ray, magnetic resonance images, and related health scans. Majority of existing solutions for scoliosis measurements are mechanical. They have constrained parameters, patch-based approaches, which loses contextual informations. Furthermore, existing methods are less effective for medical applications due to their poor accuracy and loss of detailed information during the process. Our research differs from previous studies by minimizing physical intervention by developing an accurate end-to-end approach for scoliosis severity detection using machine learning for rapid and reliable medical diagnosis, specifically for scoliosis. For our methodology, so we collected 210 grade scale 2D spinal images that exhibits scoliosis in the AP view, 1920 by 1080 pixels. So samples include complete picture of the thoracic and lumbar vertebrae. So for training, so 180. For test sets, 20, and we have 10 validation sets. So data are annotated already with expert measurement of the cub angle as references. Spinal region isolation. So the objective of this step is to focus exclusively on the thoracic and lumbar vertebrae where most scoliosis are occurring. So we reduced the X-ray images to 27.75 anatomical projection by using aggregated channel feature with LUB. So after the channel feature extraction, so we then use the ADABUS classifier to identify the regions of interest or the ROI window in order to crop the region. This is very important because isolating the spinal column will reduce or diminish noises in the images because we are only interested in the spinal region. So for the spine boundary identification, so we locate the vertebral segment using a center segment line. As you can see, the green line. We superimpose series of rectangle windows positioned at the apex of the detected spine region with 1 pixel increment as shown in figure A. Then a search is launched for the next active points between the identified pixels. As you can see in figure C, we created a 10 by 4 pixel window section with red boxes for spine delineation points, which resulted in blue and yellow dots. So next, we perform polynomial pitting for the CSL. So in figure B, then the process is repeated until all possible touch points on the center segment line is examined. So at number 6, a reconstruction of the current matching window is performed until all spine limits are identified. So we offset the center segment line in order to trace the edges of the spinal column. So for the vertebrae identification, so once the spine's edges are defined, a midpoint line is used to isolate the spine's foreground region, as can be seen in figure B. Then we created equally subspace lines to produce threshold images and values. So it's important because we want to extract, as can be seen in figure D, the identified vertebrae threshold using a 18-bin non-overlap subhistogram to derive the edges of the vertebral region. And because of the initial vertebral region, so it will be easier for the vertebral detection already in figure E. So for the vertebral segmentation, so we altered the standard unit for segmentation purposes. So the encoder side or the left side is you use convolution and downsampling. So that is the our detailed implementation. So at the right side, we use a decoder by using upsampling and concatenation. So we use residual unit, a 3 by 3 convolution with 1 by 1 convolution. So during concatenation, we upsample and we utilize a max pooling of 2 by 2. So full details of this implementation can be read on the final paper or in the proceedings. So for the vertebral segmentation, so we use a tenfold cross-validation to assess the segmentation performance. So for the hyperparameters, we use the Adam optimizer, a 0.01 learning rate, 100 epochs, 10 batch size, 0.25 drought out rate, and an L2 norm loss function. So we compared three architecture, the classical unit, our modified residual unit, and the dense unit. So for the Cobb angle calculation, so in order to identify the border box, we use an algorithm MBB, or the minimum boarding box, for the upper and lower vertebrae border. So when specific borders are defined already, all the vertebrae and plates are estimated. It is stored in an array, and we identified the most tilted vertebrae based on the equation number 3, where x is the slope of the upper vertebrae's upper border and xj is the slope of the lower vertebrae's lower edge. So for the segmentation performance metrics, so we will be using three evaluation metrics: the die similarity coefficient, the Jacquard similarity, and the mean squared error. So for the spine curvature evaluation, so we benchmark the physician's measurement versus the machine learning measurements, and t-test and mean absolute percentage error for 10 validation sets. For the results, for A, segmentation evaluation results, as you can see on the table, having a dice and Jacquard similarity of higher means that the segmentation is accurate, while a lower score for the mean squared error means that the error is less. So the residual unit on average perform better on three metrics. So for the segmentation evaluation result, so based on the training time, so the dense unit is trained the most time with 51.35 minutes. So on average, residual unit it's 34 24 minutes. So for testing time, so 0.02 seconds, 0.04 seconds, and 0.06 seconds. So for the top and bottom vertebrae reference evaluation, so as can be seen at the table, the machine learning methods deviates only at 6.6 in terms of top vertebrae identification and zero point 0.5 lower vertebrae, a very small margin of error. So for the cub angle evaluation, so based on the medical experts measurement and our deep learning prediction measurement, so we measure the absolute difference. So using a t-test, so we derive a p-value of 0.9028 with t-value of 0.1237. So it means that there's no significant difference at 0.05 levels. Also, the mean absolute percentage error of 8.18% means that it's accurate, and the only mean absolute difference for the 10 validation set average only at 1.57 degrees, which is very low. So here's the sample of the exhibit for measuring cab angle. So we use a library, drawing library in Python, and a library for measuring the specific angle of tangent lines. So for the discussion, so this research established that our approach could automatically measure cab angle using intuitive procedures. So empirical results indicate that the residual unit surpasses both the unit and dense net with segmentation accuracy of 92.95% for DSC and JS, and an error reduced by 0.975. So this is a lot when it comes to image processing. So our test demonstrated that comprehensive and optimized procedure such as spinal region isolation, spine boundary identification, vertebrae detection, and segmentation serves as a prelude to accurate cab angle measurements by an average of 91.81% by a mean absolute percentage error. So our pipeline validation was confirmed through observe against the machine learning measurement with a t-test p-value of 0.928, suggesting no significant differences between the annotated physician's measurement and our machine learning measurement. So we also noted that dense unit did not necessarily lead to accurate segmentation. So it's very complex architecture as its framework has specific strengths and weaknesses depending on its applications. So like any research, we encountered challenges of noisy X-ray scans due to insufficient image quality and patient's unbalanced posture contributing to forecast deviation. So this study did not explore algorithms for compensating these issues, such as image reconstruction, enhancement, and reorientation correction. So for the conclusion, an accurate prognosis of scoliosis severity is crucial for medical practitioners' treatment planning and decisions. So traditional methods of cab angle measurement is very time consuming. It's a manual process and it's very susceptible to discrepancies because of subjectivity of the doctors or the physicians. So we address this by developing a systematic pipeline for automatic yet accurate cab angle measurement using deep learning on residual unit architectures. We contributed to science by producing a dependable and simplified scoliosis severity identification using artificial intelligence through deep learning. Our framework can assist doctors in clinical practice to better understand scoliosis and its complementary treatments. For future work, the authors plan to improve the model's accuracy by increasing the number of training sets, a better segmentation algorithm, and evaluating other CNNs or the convolutional neural network's performance. Thank you very much for listening.